Hello everyone, this is Dr. M.K. Shukla, Associate Professor SIRTS Pharmacy, Bhopal. So today I'm going to present one topic that is radiopharmaceuticals under the pharmaceutical inorganic chemistry with the code BP104. So, under this topic, we will cover the radioactive decay, radiation units, radiopharmaceuticals, properties of an ideal diagnostic radioisotope, radiopharmaceuticals categories and production, radiopharmaceutical quality control, radiation measurement, application of radiopharmaceuticals, and journey of radiopharmaceuticals. Thank you. So, what is the radioactive decay? An unstable atomic nuclei spontaneously loses energy by emitting ionizing particles and radiation. So, this is the radioactive decay. And radioactive isotopes, first of all, so we have to take the radioisotope, and when we bombarding the some type of rays, so it converts into the parent nuclei and then the daughter nuclei. So when an unstable nucleus decays, it may give three types of rays. Like first one is alpha rays, or they are also known as helium radiation, beta rays, which also known as electron radiation, and gamma radiations. So alpha particle decays. So alpha particles are made of two protons and two neutrons. Are same. They are same as helium nucleus. When a nucleus emits alpha particles, its atomic number decreases by 2 and its atomic mass decreases by 4. These particles are generally slow and heavy. With a very low penetrating power, as they have the large charge, uh, as they have the large charge. So alpha, as they have the large charge, alpha particles ionize other atoms strongly. Also, the alpha decays occurs in very heavy elements like uranium and radium. So second is the beta particle decay. These particles are as same as the electrons, as they have the charge of -1. When a nucleus emits beta particles, the atomic number increases by 1. When a nucleus emit beta particles, the atomic increases by 1 and atomic mass is unchanged. They are fast and light. They have the very medium penetrating power. Example are radioisotope emitting beta and phosphorus 32. These particles ionize atoms that they pass, but not as strongly as alpha particles do. Third one is the gamma rays. Gamma rays are waves, not particles. They have no mass and no charge. Atomic mass and a number unchanged. High, they have the very high penetrating power. Also, they do not directly ionize the other atoms. When we don't find a pure gamma source, as they are emitted along alpha or beta particles. Useful gamma source are technetium 99, used as tracer in medicine. So these are the diagram of alpha, beta, and gamma rays. So we can see like the alpha rays has a penetrating power very low, which do not cross the paper. Also, the beta rays have the medium penetrating power, and they can pass the aluminum. They don't pass the paper, but not the aluminum foil. In case of gamma rays, they can very good penetration power. They have and they can pass paper, aluminum as well. So for stopping these and controlling the gamma rays, we have to take lead blocks. These are the properties of alpha, beta, and gamma rays by categories like charge. So alpha rays have the plus 2 charge and beta has the minus 1, and whereas the gamma don't have any charge. In case of mass, alpha has 2, beta and gamma has 0 mass. Ionization power, so alpha has the high ionization power, medium in case of beta, and low in gamma rays. And penetration in air, so they can penetrate only less than 5 centimeter. In case of beta, they can penetrate up to 1 meter, and in case of gamma, they can penetrate up to 1 kilometer. So how we can stop the alpha rays by paper, beta rays by aluminum, and gamma rays by lead blocks. So what is the half life? The half life of radioisotope is the time for the radiation level to decrease decay to one half of the original value. Naturally occurring tend to have longer half lives. Used in nuclear medicine have short half life. So we also categorize the different materials with their half lives, like radioisotopes. So 14C have the half life of 5,730 years, whereas the potassium 40 has the half life of 1.3 into 10 to the power 9 year. 226 radium has the half life of 1600 years. Uranium 238 has the power of 4.5 into 10 to the power into 10 to the power 9 year, whereas the Fe 59 Fe 46 days. And uh, so बोलो। किस चीज में तूने ये सबमिट किया असाइनमेंट वगैरह? सर वो तो असाइनमेंट आप लोगों ने सब सब तुमने किया? आए थे तुम? हाँ आया था सर, शुभम नाम है। शुभम तो नाम है। तो अभी रुक जाओ, फिर अभी मेरी एक मीटिंग है। तो हम लोग भी चले, हम लोग जा रहे हैं। कहाँ जा रहे हो? हम लोग हॉस्टल बंद हो रहा है ना, तो हम लोग को निकलना पड़ेगा। हॉस्टल बंद है, बोलते नहीं नहीं चलिए, अभी हम लोग रुक जाते हैं कुछ। लो हॉस्टल वाला सर बहुत। तो नीलमा मैडम नहीं आ रही है तो उनका क्या होगा? आपको मैं बताऊं कि डायरेक्टर सर बताएंगे? डायरेक्टर सर को मंडी को बता रहे हैं। 105 आपका थोड़ी है फोन। अरे कोई बात नहीं है, ऊपर नीचे कर 134 अनिशा से है ना, अनिशा से करवाना पड़ेगा। अनिशा को पता नहीं है, ऐसा पता नहीं हम करवाएंगे क्या। तुम अपना पेपर लाना तो पेपर ये कहाँ साइन करा दिखो आप। अच्छा ये तुमने ही लिखा है तुमने प्रिंट कराया है। गेट बंद कर दो, ढक दो। हाँ 59 Fe has the 46 days, 59 Cr 28 days, 131 iodine 8 days, 99 MTC is 6 hours. So radiation units, there are some radiation units to calculate the radiations, like Curie CI measures the activity as the number of atoms that decayed in 1 second. A rad unit is used for radiations absorbed dose, measures the radiation absorbed by the tissue of the body. REM radiation equivalent mass is the measure the biological damage caused by the different types of radiations, whereas the Becquerel BQ, one BQ is one disintegration per second DPS. Sievert SV is 100 RM equals to 100 RM. Gray GY is equals to 1 joule per kg tissue. Now the radiopharmaceuticals. So these are the medical formulations containing radioisotopes composed of two parts. First one is the radionuclide and second part is the pharmaceuticals. So nuclide, any species of atom characterized by a specific number of neutrons and protons within the atoms. What are the properties of an ideal diagnostic radioisotopes? So types of emissions. So pure gamma emitters like alpha and beta particles are unimaginable and deliver high radiation dose. So energy of gamma rays should be ideal 100 to 250 kilo electron volt keV, and photon abundance which should be high to minimize the imaging time, easy available. So they should be easily readily available, easily produced, and inexpensive. So target to non-target ratio should be high, which maximum efficiency, having the maximum efficiency and minimum the radiation. Effective highlight should so they should have the short enough to minimize the radiation dose to patient, and long enough to perform the procedure. Also the patient safety should not be exhibit toxicity to the patients. They should be prepared with no complicated equipment and no time consuming steps. Radiopharmaceuticals can be divided into four categories. The first one is the radiopharmaceutical preparation, radionuclide generator, radiopharmaceuticals precursors, and kit for radiopharmaceuticals preparations. They are manufactured manufacture in case of manufacture radionuclide production. They include it includes nuclear fission, charged particle bombardment, neutron bombardment, and radionuclide generator systems. Example of production of technetium 99. So uranium 235 is bombarded with neutrons, which splits into molybdenum 99 and other particles. Molybdenum 99 undergoes beta decay to produce technetium 99. Production of radiopharmaceutical preparations, so they can be produced by sterilizations for heat stable products, like they undergoes the autoclave. For heat labile products, they undergo using membrane filtration of the radiopharmaceuticals using 0.22 micrometer micron millipore filters, and addition of antimicrobial preservatives. The nature of a microbial preservative, if present, is stated on the label, or where applicable, that no antimicrobial preservative is present. Radiopharmaceutical production. So in this picture we can see the different parts of how we can produce the radiopharmaceuticals production, like cyclotron or a reactor is used. They goes the nuclear reactions or radioisotope production and shipment from a reactor to production facility. These material used in radiopharmaceutical grade product and from the reactor to produce production facility, and active pharmaceutical ingredient API so these three points are considered, like purifications, quality control, and dispensing. Also, pharmaceutical product should have the label if required, and dispensing, sterilization, quality control, packaging, and shipping. Radiopharmaceutical quality control, so they can be tested under identity test, The radionuclide is generally identified by its half-life, or by the nature and energy of its radiation, or by both, as is stated in the monograph. Radionuclides purity, the gamma rays spectrum should not be significantly different from that of a standardized solution of the radionuclide. Radionuclide purity can be assessed by a variety of analytical techniques such as liquid chromatography, paper chromatography, thin layer chromatography, and electrophoresis. Chemical purity can be checked, the proportion of the preparation that is in the specified chemical form, regardless of the presence of radioactivity. It may be determined by the accepted methods of analysis. The pH should be checked of the radioactive solutions. The pH may be measured using paper pH indicator strips. Ideally, should be in between 6.8 to 7.5 pH. Sterility of the radio pharmaceuticals will be checked by the radio respirometry. The samples of radio pharmaceutical is incubated in a culture media containing 14C glucose or 14C acetate at 37 degrees Celsius for 3 to 24 hours. If bacteria are present in the sample, they metabolize the 14C glucose or 14C acetate, which is measured in a liquid scintillation counter. Radio respirometry is a faster techniques for sterility testing of radiopharmaceuticals. Next one is the colony culture. The sample of radiopharmaceutical is incubated in thioglycolate media with 30 to 35 degrees Celsius for aerobic and anaerobic bacteria, or in soybean casein media 20 to 25 degrees Celsius for fungi molds. The test medium is observed for 7 to 14 days. The presence or absence of microorganisms in the sample is determined by by bacteria growth or lack of it in the culture. Now the next one is the bacteria endotoxin pyrogen testing. For bacteria endotoxin test, lal test has been performed. For pyrogen test, rabbit pyrogen test is performed. The labeling of radiopharmaceuticals should be as follows. The storage of radiopharmaceuticals should be kept in a well-closed container. Storage conditions should be such that maximum radiation dose rate to which persons may be exposed is reduced to an accepted level. And radiopharmaceuticals preparation intended for the parenteral use should be kept in glass vials, ampule, or syringe that is sufficiently transparent to permit the visual inspection of the contents. Radiation measurement. So there are many measurements, three measurements. So first one is the Geiger Muller counter. So it detects the beta and gamma radiation, uses ions produced by radiation to create an electrical current. It is gaseous ionization detector and uses the Townsend avalanche phenomenon to produce an easily detectable electronic pulse from as little as a single ionizing event due to a radiation particle. A gas ionization process where free electrons are isolated by an electric field collide with gas molecules, and consequently free additional electrons have been prepared. This is the overall Geiger counter process have been performed. Next was is scintillation counter, an instrument for detecting and measuring the ionizing radiation by using the excitation effect of incident radiation on a scintillating material and detecting the resultant light pulses. So incident photon has been introduced to the scintillator, where the light photon is available. So these passes through the cathode, and focused by focusing electrode to the dynode, and by collecting by the anode, and passes to the electrical connectors. Applications of radiopharmaceuticals: the treatment of diseases, like therapeutic radiopharmaceuticals, which also known as therapeutic radiopharmaceuticals. They are radio-labeled molecules designed to therapeutic doses of ionizing radiation with specific disease sites. Examples are chromic phosphate P32 for long ovarian, uterine, and prostate cancers, sodium iodide I-131 for thyroid cancer, Samrine SM 153 for cancerous bone tissue, sodium phosphate P32 for cancerous bone tissue and other types of cancers, strontium chloride SR89 for cancerous bone tissue, and erbium 169 for relieving arthritis pain in synovial joints as an aid in the diagnosis of diseases. So, diagnostic, which also known as diagnostic radiopharmaceuticals. The radiopharmaceuticals accumulated in an organ or interest emit gamma radiations, which are used for imaging of the organs with the help of external imaging device called gamma camera. Radiopharmaceuticals used in tracer techniques for measuring physiological parameters, for example, like 51 CR EDTA for measuring glomerular filtration rate, and radiopharmaceuticals for diagnostic imaging like 99M technetium methylene diphosphonate MDP, used in bone scanning. PET is also used, like what is PET? PET is positron emission tomography, and SPECT single photon emission tomography are imaging technologies that enable physicians to diagnose different types of cancer, cardiovascular diseases, neurological disorders, and other diseases in their early stages. So there are difference between PET and SPECT. In PET involves positron. In case of SPECT, it involves gamma rays. PET is more sensitive, high resolution detection to PET scanner, expensive scanner, limited half-life of radiopharmaceuticals. In case of SPECT, it involves gamma rays, optimum sensitivity, lower resolution detection by gamma camera, and cheaper than PET, and longer half-life of radiopharmaceuticals. This is the journey of radiopharmaceuticals. So, radionuclide generation first it's happened by cyclotron, nuclear reactor, and radionuclide generator. Then these things are going to the radio tracer production by synthetic biomolecules coordination complexes and salts. Then patient exposure has been performed, in which these things are introduced to the patient by injection or ingestion. These things are then going to radioactive decay by isometric transition spect, electron capture spect, and positron emission PET, and annihilation by PET. Annihilation by PET. And then the gamma rays detection is covered by Anger camera, which is in aspect and ring of detects by PET. Then the image reconstruction have been performed by iterative reconstructions. Thank you so much.